Hi, my name is Yiwei. I'm a PhD student of mechanical engineering, and today my presentation is a simple relation between stiffness and swelling of a hydrogel. Now let's get started. What are hydrogels? Hydrogels are polymer networks that absorb water and not dissolve in water. Actually, we can see hydrogels almost every day, like noodles or rice. We can call them starch-based hydrogels. And hydrogels are beneficial for a variety of applications, such as drug delivery, eye contact lenses, or even in diapers. And most applications of hydrogels are based on the relationship between mechanical stiffness and water swelling behavior. For instance, we are cooking some noodles. The longer time we cook, the softer will be the noodles, because as time goes on, the noodles will swell more and more water. But if we leave the cooked noodles at the table, let's say for 1 hour or 2, it will lose water, so get dried, and at the same time, it will be stiffer. So this is the relationship. And today, my presentation will focus on both of these two very important properties of hydrogels. To be honest, there have been already a lot of brilliant works about hydrogels, especially the hydrogels properties. However, hydrogel studies on stiffness often limit analysis to the fully wet state or fully swollen state, as shown in the figure, because this state is easier to be reached and more stable for test. But what about 50% fully wet, or let's say 10%? Is there a relation between stiffness and swelling of hydrogels at all states? That was our first question. And as we know, the relative humidity from the ambient environment can influence the swelling behavior of a hydrogel, and of course the stiffness. But the exact dependence on humidity of stiffness and swelling remains an open question. Is that possible for us to build up a system or maybe a simple equation to describe this dependence? So how does humidity influence stiffness and swelling of hydrogels? That was our second question. To answer the first question, we made two assumptions. We assumed hydrogels fit Dejean's semi-dilute polymer theory, and also hydrogel can be treated as a poroelastic system. By combining the equation and the expression from both of our assumptions, we can directly relate the stiffness modulus K of a hydrogel to its polymer volume, the V poly. And also we define the swelling fraction to be V over V wet, and V wet is the volume of a hydrogel at fully wet state. By combining all the equations and the expression shown on this slide, we can make a very simple scaling law, which is K over K wet equals to S to the negative 9 over 4. And this scaling law is experimentally testable. That means if we can confirm this scaling law, it also means we verified both of our assumptions, and that means question 1 is answered. So to determine the stiffness, we were using a custom indentation system, which is shown on this slide. And the samples we used were pure PEM hydrogel, and we controlled cross-linker ratio from 1% to 3%. Now let's check the result. After I plotted the ratio of K over K wet, the stiffness at fully wet state, versus the swelling fraction S, we can find all the data points just locate along with the slope of negative 9 over 4. And if we look at the y-axis, it is in log scaling. That means we confirm the power of this, the swelling fraction of our data was negative 9 over 4, and that also means we successfully confirmed our scaling law, and also means we successfully verified both of our assumptions. So now we can say mission 1 is completed. To answer the second question, actually we divided this question into 2 parts. How does humidity influence the swelling, and how does it influence the stiffness? For the swelling part, we were using a custom humidity control system, which is shown on this page, to determine the equilibrium swelling fraction of all the samples. And in this experiment, we didn't just limit the type of a hydrogel to be the pure PEM hydrogel. We also modified the samples by adding some DMA as filler or apply hydrolysis as post-treatment. So now we have 3 different types of hydrogel. And from this figure, we can clearly say as the decrease of relative humidity levels, the equilibrium spelling fraction of all the samples decreased as well. And this is what we expected, and we just need to confirm it. For the stiffness part, we quantify the change of osmotic pressure delta pi with relative humidity RH. This quantification was inspired by a Harvard group's work, which confirmed that the osmotic pressure of a hydrogel is independent of its cross-linking. So that's why in the expression on the left side, there is a VW. VW is effective solvent molecular volume, or in an easier way, we can say it indicates how water molecules are packed within the polymer mesh. So we hypothesize that if the samples are from the same hydrogel family, they should have very similar or even the same polymer mesh. So that means the values of VW of all these samples should be very similar or even the same. So back to the expression, the delta pi value of all the samples from the same hydrogel family should be only dependent on the relative humidity RH. Now let's check the result. Here are the data points for pure PEM hydrogel and the samples with DMA as filler and hydrolyzed samples. From this figure, we can make two conclusions. The first one is just in contrast to that of the equilibrium swelling fraction, as decrease of relative humidity, the delta pi value, the change of osmotic pressure of all the samples, increased. That means all of them get stiffer. This is what we expected, and we confirmed it. And another conclusion is very important, that we successfully confirmed our hypothesis that if the samples are from the same hydrogel family at the same relative humidity level, the delta pi value of all the samples should be the same. And that also means we can use the change of osmotic pressure delta pi to identify the family or a type of a hydrogel. And this is what we got for the stiffness part. So mission 2 is completed. But actually, we didn't stop there. We just got a very interesting or a little bit crazy idea that is that possible for us to mix all the equations or the scaling laws we just made to make a final edition of the scaling law. So this is what we made as shown in this slide. And as I just introduced, the delta pi value can be used to identify the family or the type of hydrogel. So that means this final edition of the scaling law has a potential for some prediction. And now let me show you guys how we played with it. First, we tested the data points for pure PEM hydrogel with 1% cross-linker ratio, or pure 1% for short, as reference data. And with the scaling law, we can calculate or predict data for pure 3%. And now we can see how close are the actual data and the predicted data. So this result confirmed that our scaling law has the potential for the prediction. And it also gave us a very strong confidence that we can use this equation and the reference data to predict the whole family of pure PEM hydrogel. So we made this figure. That means we can predict the data points for all the samples from the pure PEM hydrogel family at all relative humidity levels. And to confirm the feasibility of our scaling law in different types of hydrogel, we apply the same process onto like the DMA samples and the hydrolyzed samples. So now totally we have 3 different hydrogel families. In each family, we have 5 different cross-linking densities from 1% to 3%. And totally we have over 120 separate verifications of prediction. And from the figure, we can see how close they are. And after the calculation, the error of all the predictions were all within 20%. And because we were using the log scaling, and that means 20% was actually very, very small. And I am sure that if I could reduce or further reduce the uncertainty of the experiment, we can even reduce this error down to maybe 10% or even 5%. And now we can say we made it and the final mission is completed. As a conclusion, our scaling law can give us a better understanding of hydrogels and make the gel synthesis and analysis more efficient. And also we believe our scaling law can be a guidance of hydrogel applications in the future. And currently I'm working on how how relative humidity influences permeability of a hydrogel, and also our work is building up a hydrogel-based water harvesting system. If you guys are interested in our work, please visit our website or just simply Google UNLV. That's all for my presentation. Thank you.